Welcome to AI Frontiers. Today we explore revolutionary robotics breakthroughs that are reshaping intelligent machines. On June 18, 2025, 17 groundbreaking papers were published in Computer Science Robotics, presenting advances that transform everything from disaster response to space exploration. These aren't incremental improvements, they're revolutionary systems that can glide across water at 8 meters per second, dive underwater for deep exploration, and launch into the sky for aerial surveillance, all in one integrated platform. Picture this scenario that seems impossible yet is now reality. A single robotic platform glides across the ocean surface at nearly 8 meters per second, then seamlessly transitions underwater for deep exploration, and finally launches itself into the sky for aerial surveillance. This isn't science fiction anymore. 17 papers published on a single day in June 2025 demonstrate that such multi-environment capabilities are now achievable. These systems represent the convergence of advanced artificial intelligence, sophisticated mechanical design, and intelligent control systems, working together to solve real-world challenges. These discoveries represent revolutionary advances that extend far beyond incremental improvements. The research transforms applications from disaster response and space exploration to underwater research and daily life assistance. By the end of today's exploration, you'll understand not just what these robots can do, but why these breakthroughs matter for our future. We're examining how these systems solve problems we didn't even know existed, bridging the critical gap between controlled laboratory environments and unpredictable real-world deployment scenarios. Computer Science Robotics serves as the intelligence layer behind modern robotic systems. While mechanical engineers design the physical structure and electrical engineers create the control systems, computer scientists develop the software intelligence that makes robots truly smart. Think of it as teaching a sophisticated puppet not just to move, but to think, learn, and make decisions in a world full of uncertainty and complexity. This field sits at the intersection of artificial intelligence, machine learning, computer vision, and control theory, creating the software intelligence that enables robots to perceive their environment, make decisions, and execute complex tasks autonomously. The significance becomes clear when considering the transition from controlled factory environments to unpredictable real-world scenarios, like homes, hospitals, disaster zones, and public spaces. It's like the difference between playing chess with perfect information and navigating a busy city street where anything can happen at any moment. The first major research theme focuses on multimodal locomotion and environmental adaptation. Researchers are moving beyond the traditional approach of building specialized robots for specific environments. Instead, they're creating versatile platforms that can adapt to diverse operational contexts. It's like designing a Swiss Army knife instead of individual tools, one device that can handle multiple challenges. The SurfAAV project exemplifies this approach, presenting a vehicle that can navigate underwater, glide on water surfaces, and fly through the air without requiring complex buoyancy systems. This represents a fundamental shift from specialized single-environment robots to adaptable multi-domain platforms. Advanced perception and mapping systems form the second critical research theme. Modern robots need sophisticated environmental understanding to operate autonomously. Think of this as giving robots not just eyes, but the ability to truly see and understand their world. The MQ-SLAM system demonstrates this advancement with its multi-camera omnidirectional approach, creating detailed maps that include not just geometric information, but semantic understanding of what objects are and how they relate to each other. These systems provide the foundation for autonomous navigation and intelligent interaction with complex environments. The environmental context and object relationships enable robots to make informed decisions about navigation paths and interaction strategies. The third theme centers on intelligent manipulation and interaction strategies. Robots are evolving from simple pick-and-place operations to sophisticated manipulation tasks that require understanding object properties, environmental constraints, and task objectives. It's like the difference between a player piano that can only play pre-programmed songs and a jazz pianist who can improvise based on the audience and atmosphere. This evolution includes advances in human-robot interaction and communication, where robots learn to adapt their behavior and communication style to different contexts and users. The manipulation systems now incorporate multimodal sensing that more closely mimics human capabilities, combining vision, touch, and force feedback for robust object handling. Several papers present findings that represent significant breakthroughs with implications extending far beyond their immediate applications. The SurfAAV system achieves remarkable performance metrics, reaching surface gliding speeds of nearly 8 meters per second and underwater speeds of over 3 meters per second without complex buoyancy adjustment systems. The SHeRLoc system achieves an order of magnitude improvement in heterogeneous radar place recognition, increasing recall from below 0.1 to 0.9. The robust instant policy system demonstrates at least 26% improvement in task success rates compared to existing methods. Whole-body contact manipulation systems for humanoid robots show that incorporating touch feedback significantly improves manipulation robustness. Finally, training-free zero-shot navigation systems demonstrate high performance without task-specific training. Today's featured paper, the SurfAAV project led by Liu and colleagues, presents a groundbreaking approach to multi-environment robotics that could revolutionize exploration and monitoring applications. The story begins with a fundamental problem that has plagued robotics for decades. Traditional robots are like specialists in a world that demands generalists. If you need to monitor a marine environment, you typically deploy separate systems: an underwater robot for the depths, a surface vessel for the water surface, and an aerial drone for overhead surveillance. Each system requires separate deployment, maintenance, and operation, creating logistical challenges and limiting operational scope. The research team asked a deceptively simple question: what if one robot could do all three effectively? The breakthrough came from reconceptualizing the entire approach through differential thrust vectoring hydrofoil design. Think of it as a wing that works in both water and air, but with intelligent control that adapts its function to the current environment. This isn't just clever engineering, it's a fundamental shift in how we approach multi-environment operation. The hydrofoil system generates dynamic lift for high-speed surface gliding, much like how a speedboat's hull lifts it partially out of the water at high speeds. The same system reconfigures for underwater propulsion, where the hydrofoil acts more like a fish's fin, providing both thrust and maneuvering capability. For aerial operations, the system leverages surface speed to achieve gliding takeoff, transitioning from water-based lift to aerodynamic lift. The real-world validation demonstrates the system's practical capabilities. The SurfAAV achieves a maximum surface gliding speed of 7.96 meters per second. That's nearly 18 miles per hour on the water surface. The underwater speed of 3.1 meters per second represents efficient underwater navigation that many dedicated underwater vehicles struggle to achieve. Most importantly, the system successfully demonstrates transitions between all three operational modes, including the challenging gliding takeoff from water surface to aerial flight. Environmental monitoring applications could deploy a single SurfAAV system to conduct comprehensive surveys across multiple environmental domains. Search and rescue operations could use these vehicles to rapidly transition between aerial searching, surface navigation, and underwater recovery operations. Looking ahead, the computer science robotics field stands at an inflection point where multiple technological advances are converging to enable previously impossible capabilities. The integration of advanced artificial intelligence with sophisticated mechanical systems, the development of robust multimodal sensing, and the creation of adaptive control systems are combining to produce robots that can operate effectively in the complex, unpredictable real world. The trend towards general-purpose, adaptable robotic platforms represents a fundamental shift in how we approach robotics. Rather than building specialized tools for specific tasks, we're moving toward creating intelligent platforms that can adapt to diverse challenges. It's like the evolution from single-purpose tools to programmable computers. The real power comes not from what they can do initially, but from what they can learn to do. Today's journey through cutting-edge research in computer science robotics reveals a field in rapid transformation. From robots that can seamlessly transition between air, water, and underwater environments, to systems that learn from human demonstrations and adapt to new challenges, we're witnessing the emergence of truly intelligent machines. These advances in multimodal locomotion, sophisticated perception, robust learning, and secure operation are not just incremental improvements, They're foundational changes that will enable robots to tackle challenges we can barely imagine today. The 17 papers we've explored represent more than academic achievements. They're blueprints for a future where robots work alongside humans to explore the deepest oceans, respond to natural disasters, assist in our homes, and push the boundaries of what's possible. This analysis was created through artificial intelligence synthesis using Claude's Sonnet 4 model, with text-to-speech synthesis powered by Deepgram technology and image generation through OpenAI systems. The content underwent human expert review to ensure accuracy and accessibility. While we strive for comprehensive coverage, potential oversights may exist, and we encourage consulting the original research papers for complete technical details. All references to source materials are provided to support further exploration of these fascinating developments in robotics research. I encourage you to dive deeper into these papers yourself. Visit the archive preprint server and explore the detailed methodologies and results. Share your thoughts about which applications excite you most on social media using the hashtag #AIFrontiers. The future of robotics is being written today, and these papers are the opening chapters of that story. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.